All right, how to take over the universe in 3 steps. Rational animation. Okay, that sounds cool.
Let's take over the universe in 3 easy steps. Welcome. We've heard that you want to take over the universe. Well, you've come to the right place. In this video, we'll show you how to reach as many as 4 billion galaxies with just a few relatively easy steps and 6 hours of the sun's energy. Here's what you need to do. 1. Disassemble
4 billion galaxies is a lot. That's a hell of a lot. You know, we think, what, like 100 billion galaxies in the universe, but actually now looks more like 2 trillion. 4 billion is a substantial proportion of that. But I want to see what he says. Not going to lie, you make physics fun, as it should. Oh, thank you. Yeah, just trying to make things fun, eh? Goes down, it's because YouTube doesn't like learning. Yes. This is great video for distant alien military force observing us on standby. They could be. They could be watching.
Mercury and build a Dyson swarm, a multitude of solar captors around the sun. 2. Build self-replicating probes. And 3. Launch the self-replicating probes to every reachable galaxy. In science fiction, humanity's expansion into the universe usually starts...
It's not exactly taking over the universe, though, is it? I kind of wasn't listening as well. I was half listening. Did he say AI? Are the robots AI? Because in that case, well, then, yeah, I guess.
...starts within our galaxy, the Milky Way. After a new star system is occupied, humanity jumps to the next star, and so on. And
if I'm, you know, have to go to space someday, I want that. I want that starship. Get me the cat ship. We're going to call it Cygnus after my famous cat. Clickbait. Well, I mean, not exactly. Like, what he said is true. So we'll talk more about this. Like, what he said could all be done. The Dyson swarm, sending it around, you could do that. And the 4 billion galaxies, though, that's debatable. Because if you're sending a physical object... No, don't retract it, man. You have a point. Because, like, if you're sending a physical object, to propel that to near the speed of light, which is what you'd have to do to get these things anywhere near that many galaxies, that would require enormous energy. And I get it. He's going to say with the Dyson swarm, you know, direct it, you know, into some, you know, like laser-powered solar, you know, thing, you know, solar reflector thing that powers a solar sail. But we'll see.
Galaxy. Then humanity jumps to the next nearest galaxy, and the process is repeated. This is not how we're going to do it. Our method is much more efficient. We're going to send self-replicating probes to all the reachable galaxies at once. Getting to the furthest galaxies is not more difficult than getting to the nearest ones. It just takes more time. When a probe arrives at its destination galaxy...
That doesn't make a lot of sense. It is more difficult because of something called dark energy, my friends. So the universe is expanding, right? And the further you look, the further away, the more it's expanding. How does that not make it more difficult? And not only that, I get what he's saying. You know, these things are robots, so it doesn't matter too much if they're further away. Yes, but you still need, when things are very far away, you know, because it's a vacuum, you might think they just travel forever at that speed, but that's not actually necessarily true because there are things in space and small amounts of things, and a craft will slow down over a long period of time. And so you will need to give it, you know, like energy boosts. A lot of people don't consider that. Let's keep going.
It will search for a planet to disassemble, build another Dyson swarm, and launch a new wave of probes to reach every star within the galaxy.
Okay, so you're going to need something that's artificially fairly intelligent.
And then each probe in that galaxy will restart civilization. We already hear you protest, though. This whole thing seems pretty hard to me, you say, especially the disassembling Mercury part. But actually, none of these steps are as hard as they first appear. If you analyze closely how they could be implemented, you'll find solutions that are much easier than you'd expect. And that's
I agree with that. They are easier than people expect, and you could disassemble Mercury to create a Dyson swarm in theory. If it's practical, I guess, you know, we'll see. Maybe we might be able to create some simulations to see if it actually is somewhat practical. I mean, it looks like it is.
Exactly what Stuart Armstrong and Anders Sandberg do in their paper, Eternity in 6 Hours, Intergalactic Spread of Intelligent Life and Sharpening the Fermi Paradox. This video is based on that paper. Exploratory engineering and assumptions. What we mean by easy here is that we will require amounts of energy and resources that are small compared to what is at our disposal in the solar system. Also, the technology required is not extremely far beyond our capabilities today, and the time required for the whole feat is insignificant on cosmic scales.
Well, yeah, so we haven't talked about this yet, but he's saying you can reach very distant galaxies basically because of relativity. So for these things that travel near the speed of light, time slows right down for their clocks. For, people relative to them, observers, that's not the case. But for the things traveling very, 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 very close to the speed of light, yeah, their internal clocks do slow. And not only that, space contracts. And at speed of light, space contracts to zero, and time stops. And you've probably heard me talk about this already. Like, light is everywhere and anywhere instantaneously. That's the current understanding in physics. It doesn't sound like it makes a lot of sense, but if you go through that path of physics history, you can actually understand it. So that's how you can get anywhere very quickly. But that's a problem. You can't do, because if you do that, yeah, for you time slowed down and you can get over there, but everyone you knew is dead, right? Yes, they're robots, so they don't care about that, right? And you could just colonize. What would be the point of that, though? Like, consider if we had the means to do this. What would be the point if you can never, like, reap any rewards or anything from it at all? So it's like, okay, just imagine, for the sake of argument, you could do this, okay? And it's like, we could now push this button and launch these probes that are really intelligent out there, and they would do this and self-propagate to other galaxies, and we could colonize, you're not really colonizing, but just spread these things all over the universe, some of it, not all of it. And what would be the point of that? Because you can't actually get anything out of it. Do you see what I mean? Like, are you just trying to kill or like start life elsewhere? Maybe that's what you're trying to do. And then, okay, well then, yeah, let's do it. But in doing that, you'd want to make sure these probes are not going to just eat planets that already have life on it, right? And how do we know that life isn't pretty much around every star system? We don't yet. And it could be the case. So if you just send these things out without knowing that, you're potentially killing all life. And yeah, then it's going to reemerge. You're going to plant it, panspermia. But what if it's already there? You're just committing mass genocide. And if there's a god, you're pretty stuffed, right? So it's like, I don't know if any reasonable species or thing would do this. Sure, one that had different tendencies to us probably would, if they, that's what they wanted to do, I guess. Just basically fighting against the eventual heat death. Yeah, the heat death just renders everything like pointless, doesn't it? Got to do something, right? And like Elon's always talking about, he just wants to spread consciousness around. A light is a straight line traveling through space-time. Light is a straight line. Absolutely not, my friends. I mean, it's trying to travel in a straight line, but space-time itself gets curved all over the place and warped when there's mass and energy around. And so this is why people tell you to imagine space-time as a flat sheet. You can't. This analogy actually doesn't work. But if you do it, and you put mass in there, and you can imagine it bending, and then, if you try and put light, which is traveling through space-time, through this space-time now that's curved, it's going to curve, right? So light, it actually technically is following a straight line, but if it's kind of not, if you're following, right? Light is always trying to follow a straight line, but it follows what are called geodesics, which is a straight line in curved geometry. And that's what's going on. So in a sense it is, and in a sense it's not. So it's like a particle is both a wave and a particle at the same time. However, that is kind of an outdated look because, quantum field theory says no. It's all of this other stuff, this wave stuff, but not really a wave in the wave you might be thinking, like classical waves, like waves at the beach. That's not the waves they mean in quantum field theory. And there's really no analogy to even actually saying it's a wave is so inaccurate. And I do it sometimes just because how else are we going to talk about it? So someone asked, any news about CalVPN? Update on CalVPN. It's broken. It doesn't work. I'm kidding. Everything's going really well. So like I said in the last stream, but if you missed it, I'm creating this new kind of VPN. It's not like other VPNs, right? It's called a post-quantum VPN. It has things in it called post-quantum cryptographic algorithms, and they theoretically can protect you guys from quantum computers. How it has these really difficult mathematical problems within the encryption. So updates for everyone who had like watches regularly. Everything is basically ready. Okay, so we're ready to roll out, but we're just doing all these last checks, fixing some bugs. So the Windows, the beta will be out next week. And if you're new around here, you can actually use it for free right now. The alpha is out. So if you go to the website, kelvpn.com, it's probably in my bio, you can download it, use a free VPN. It's like, there's only one country at the moment, but the beta will have like 10 different servers. Okay, sorry, I was
Not every
stuck on the comments for a while. Let's watch.
potential future technology will make sense to include in our plan to spread to the stars. We need to choose what technologies to use by reasoning in the style of exploratory engineering, trying to figure out what techniques and designs are physically possible and plausibly achievable by human scientists. The requirement, physically possible, is much easier to comply with than achievable by human scientists. Therefore, we introduce two assumptions that serve to separate the plausible from the merely possible.
I would argue that doesn't make a lot of sense, right? Because physically possible inventions completely dependent on your snapshot in time, like wherever we are in time. And achievable, oh wait, I thought that just changed. So basically to me, I think they kind of mean the same thing. They're both very hard to predict. Programmable matter, quantum computers, computronium. That's cool.
Therefore, we introduce two assumptions that serve to separate the plausible from the merely possible. First, any process in the natural world can be replicated with human technology.
Separating plausible and possible doesn't make a lot of sense to me. Same thing, right? Doesn't make a lot of sense to me. But I get what he's trying to do, but if something's plausible, it's also possible.
This assumption makes sense in light of the fact that humans have generally been successful at copying or co-opting nature. And second, any task that can be performed can be automated. The rationale for this assumption is that humans have proven to be adept at automating processes, and with advances in AI, we will become even more so.
I don't know if I like that argument either, but we'll just take that assumption. If I don't know about that.
Design of the Dyson swarm. Now, we've said we're going to launch probes to every reachable galaxy.
Obviously, it is the case if AGI is possible, and it looks like AGI is possible. So that is like technically automating, right? You're automating consciousness. But I say not because I don't count that as automating, right? That is, at that point, is what we are, and we don't say humans are automated. Unless you're one of those people and you want to think everyone's an NPC, which we might be. Penrose. Yeah, Penrose is cool. And yeah, we talked about that yesterday. Let's keep going.
This means 100 million to 100 billion probes. Where do we get the energy to power all these launches? We don't need to come up with exotic sources of energy we can't picture yet. We can use the sun itself. That's why we're going to build a Dyson swarm. To be fair, in order to be sure that a Dyson swarm will be sufficient, we need to already have plausible designs for probes and launch systems in mind. But this is a tutorial for pragmatic wannabe grabby civilizations, so we'll get to that later when we actually use them. A Dyson swarm is simply a multitude of solar captors orbiting around the sun. The easiest design is to use lightweight mirrors, beaming the sun's radiation to focal points, where it's converted into useful work, for example using heat engines and solar cells. A Dyson swarm has major advantages compared to a rigid Dyson sphere. A swarm isn't subject to internal forces that might make it collapse, and it can be made with simple and conventional materials. Even a swarm isn't without potential problems, though. The captors have to be coordinated to avoid collisions and occluding each other, but these are not major difficulties. There are already reasonable orbit designs in today's literature, and the captors...
Someone said in the comments, plausible is something like more reasonable or probable. Yeah, and I was going to say, like, I guess if you imagine, like, this is just semantics, right? Like, if you take plausible to mean something that's more likely, sure, they're different. But plausible to me, I always used it as something that's just possible. So obviously I had the wrong definition of plausible, if that's what it means. But anyway.
will have large amounts of reserves at their disposal to power any minor course correction. The efficiency of the captors will not be an issue either. We'll need only a small amount of energy to power our expansion into the universe, compared to the energy a Dyson swarm will be able to collect. The biggest problem to solve is how to get all of the material necessary to build the solar captors. Even assuming the lightest design achievable with today's materials, that is, lightweight mirrors, you'd need to take apart Mercury to get everything you need for the swarm. And that's exactly...
So Kurzgesagt made an exact video about this, right? Literally breaking down how to do this. And this was only posted 11 days ago. So he's probably, you know, inspired by that. And we made that Dyson Swarm, Dyson Sphere video, so you can go check it out on the channel.
What we're going to do. There are potentially other pathways to get the material, but being able to take apart Mercury is the conservative assumption to make, as weird as it sounds. We're not assuming future supermaterials that would let us build a swarm with extremely thin and efficient captors, and therefore with way less material. Mercury looks very convenient to use in comparison to the other planets and the...
Okay, I'm going to skip the design of the Dyson Swarm because you could go check out that video if you want. Disassembling Mercury, that's in there as well. Design of the probe, that's in there as well. The launch phase. After the universe, the galaxy. Okay, yeah, we'll get to these bits because if you want to hear about how to do just the Dyson Swarm and making the probes, the only concern about the probe is like how intelligent they are. Disassembling Mercury, yeah, this is actually possible. It not with current tech and things, like you need lots of innovation. And the Dyson Swarm is not something that might even be practical, but it looks like it theoretically is possible, right? So let's go over here. The launch.
The launch phase. Alright, now let's say we've chosen a viable design for the probes. Their construction has taken little material compared to the Dyson Swarm. The final combined mass of all the probes, redundancy included, is in the order of 10 to the 11 to 10 to the 12 kilograms. This is about the mass of a mountain. The Dyson Swarm is operational and provides us with all the energy we need. It is time to launch the probes. We'll not use rockets, but a fixed launch system. Rockets would be needlessly difficult and inefficient to use for achieving acceleration to relativistic speeds. They need to carry fuel, which would in turn need to be accelerated.
So this is also in those other videos about moving star systems around, but let's see if there's something else, because I think you'd need something better.
And the fuel needed increases exponentially with the change of speed we want to achieve. Fixed launch systems sidestep this, and are often reusable. For example, we could use coil guns. Essentially long barrels around which coils are arranged and switched on and off with precise timings, causing the probe in the barrel to accelerate due to the magnetic forces generated by the coils. With coil guns, we could shoot our probes into space.
So it's like rail guns, if you've never heard of those. I did a video on the Halo, and we did some calculations about rail guns out of that game. You should go check it out.
Combination or by themselves, we can also use solar sails accelerated by lasers or particle beams. Now look at this table. For each type of probe and for each type of replicator, you can find in bold the time required to power the launch if the energy of the Dyson Swarm were entirely devoted to the task. In the case of the 30-gram replicator, the numbers are insignificant on a human scale. 6 hours of the sun's energy is the maximum we would need. Instead, if the replicator is the 500 tons version, we would need hundreds of years of the sun's energy. But this also looks very feasible if you consider that humanity might survive millions of years, and over time might divert some energy of the Dyson Swarm to power launches, and not necessarily launch all the probes at once. After the universe, the galaxy. Now picture a future president of the solar system proclaiming, "Everyone turn off your virtual reality sets for 6 hours, we're taking over the universe." The probes are launched to every reachable galaxy, and the travel begins. Once this first wave is en route, we can launch a new wave of probes within the Milky Way at lower speeds. So we'd start expanding into our own galaxy only after having started expanding into the wider universe. Meanwhile, the probes we've launched to other galaxies will progressively continue to start new civilizations for the following 10 billion years. And after that, our expansion will be complete. 10 billion years may sound like a lot, but the universe will last for trillions of years. Future humanity will have plenty of time to enjoy even the most distant galaxies. Armstrong and Sandberg calculated that at speeds between 50% and 99% of the speed of light, the probes will reach 116 million to 4 billion galaxies.
Oh, that's a big difference. The lower estimate there, 116 million.
The higher the speed, the more galaxies the probes can reach, because the universe...
If you didn't know, it's something like 97% of all galaxies in the universe are already out of our reach, even if you were traveling at pretty much light speed. So there's that to consider. So I think these calculations look okay. Like they sound like it's from an actual paper. So
universe is expanding at an accelerating pace, and as time passes, an increasingly large number of galaxies become forever out of reach if we can't find a way to sidestep the speed of light limit. Final considerations. And now that every step is complete, you know how to take over the universe. You don't need to do everything exactly this way, though. This paper proposed many possible designs and methods at each step, but there are certainly many more ways to go. Moreover, Armstrong and Sandberg used conservative assumptions. The real designs will probably be better. The point of the paper was to illustrate that the feat is in principle possible, with cosmically insignificant amounts of time and energy. One additional point motivating the paper is that since spreading through the universe doesn't require a lot of resources, that means that the Fermi paradox is a lot sharper than we imagined. There are millions of galaxies that could have potentially reached us by now, and yet
There could be something that they're talking about that is actually just not theoretically possible, thereby actually saying, no, this doesn't, give us any answers to the Fermi paradox.
Projects in our local neighborhood. This could simply mean that there's pretty much no one else out there. Or another answer could be the one given in the Grabby Aliens videos. If we could have seen aliens, they would be here now instead of us. If there are indeed aliens out there, that means our time to begin expanding into the universe is even more limited than we previously thought. Not only is the universe expanding at an accelerating rate, making more and more galaxies forever out of reach, but aliens might also be out there grabbing galaxies instead of us. So what are we waiting for? Let's go and do it ourselves. Let's take over the universe.
That wasn't exactly a strong reason to go take over the universe, but okay. So I'm not sure I agree that it's possible in principle. There was a part here that did he even cover? I might have missed it. How to get these things out there so quickly, or I think he just skimmed over it and said the paper said it's possible. Turn on cheats in the universe settings. Yeah. But no, I think this could be possible. I just missed some stuff, or he didn't explain it. But yeah, the video was good. It was mostly pretty correct info. I thought that was pretty cool.